start with number 8. Helicopter is descending vertically with the speed of this. You guys understood the red numbers. Everyone has different red numbers, right? Good. At a height above this, for the earth, the package dropped from a window. How much time does it take for the package to reach the ground? And they give you this hint. V naught for the package equals the speed of the helicopter. All right? So, number 8. I'm going to use that V equals V naught plus V naught delta T plus 1/2 A delta T squared. And because I'm only worried about the displacement, I know that the package starts here, goes up, stops, turns around, and then comes all the way down. But since I'm only worried about the displacement, it really doesn't matter to me what it does in between. All that matters is where it starts and where it ends up. So I know where it's going to end up. I'm going to call down here 0 meters, and I'm going to say down is positive. Is that okay with everybody? Just to be weird. So I know it's going to end up at 0 meters. It's starting at negative 150 meters, I think. All right, let's see. Yep, for me it's 150. Then it's moving upwards at 1 meter per second. So I have minus 1.0 meters per second. And I don't know the time, right? That's what I want to know. That's a good thing. Delta T plus 1/2, 9.81 meters per second squared, delta T squared. Yep, that'll do it. Solve for delta T. And I would say probably the easiest way to solve for delta T would be to put that into your solver on your calculator, or if you're working on the computer, just throw it into Wolfram or something like that, right? It's a good idea to practice with your calculator since you have your calculator on the exam, right? I mean, you could go through all the algebraic steps and find what it is because you only have one variable, but so. All right, so I use Wolfram. Of course, you get 2 answers. I'm going to use the positive one, right? So 5.63. Let's see if that's right. It doesn't do that. Kind of neat though, if maybe get it right, you get the rocket call. All right, number 7. An unmarked police car is traveling a constant 115 kilometers an hour. Probably want to put that into meters per second right away. Passed by a speeder traveling at 140 kilometers an hour. Precisely 1 second after the speeder passed, this car steps on the accelerator. The car's acceleration is 3.0 meters per second squared. How much time passes after the speeder passes? How much time passes after the speeder passes before the police car overtakes the speeder? Still moving at a constant speed. All right. So I need the 2 cars to end up in the same place at the same time, right? I mean, if I was to graph it real quick, the speeder would look like that, and the police car would look like that, right? Notice I didn't have them start together down here because he starts 1 second later. And I'm wondering what that time is. I could actually do it based on their equations here, graphically, because they would end up with the, we could do it let's do it mathematically. Let's see, the speeder, for the speeder, again, I'm using my general kinematics equation, right? For the speeder, d naught plus v of the speeder delta t, and then it's not accelerating, so I just have 0 here, right? For the speeder? Yes, no, maybe? Okay. For the police, D again, because they're going to end up same slot. D naught, which I think for both of these we'll call D naught 0. Plus, they start from rest, plus 1/2 acceleration of the police, delta t squared. And actually, this should be delta t of the police, and this should be delta t of the speeder. Because they travel for different amounts of time, right? Yeah. So we know that delta t of the speeder plus 1 second equals delta t of the police. For the initial velocity of the police, because they're sitting there and they start from rest. You notice I'm zeroing for the acceleration of the speeder? Okay. And now we have 3 equations. They want to know, let's see what they want to know. How much time? Okay. Now, do they want... So they want to know the time for the speeder, actually, right? Is that right? How much time passes after the speeder passes before the police car overtakes them? So that would be the time for the speeder, right? Not the time for the police. Oh, yep, sorry. You could. So you could do it this way. Because really the only thing you don't know is time. Wait a minute, this is minus. That's minus. You could also do them from relative velocities. You can solve these 3. Let's take a look. Let's say, okay, let's look at it from the idea of relative velocities. I'm going to draw a little picture here to help us. Here's our police car. Here's our speeder. We have tail fins, I don't know. And let's take it from the frame of reference of the speeder. All right. So from the frame of reference of the speeder, the initial velocity of this cart would be the velocity. It'd be negative. It'd be the velocity of the speeder minus the velocity of the police, right? Because it's going slower, so it's going to be in the opposite direction. They're still going to have that same acceleration. Of course, this is going to be fixed. And the acceleration would be the same for both frames of reference. It would only be different if the speeder. So that kind of simplifies things. If that's fixed, it's how long it takes them to get there. Right. So I'm going to call this the velocity of the police with respect to the speeder. All right. So if we're calling this position 0 meters, don't forget we got to do all the conversion with the velocities over kilometers per hour to meters per second before we get too far. The distance here that you began at would be that distance would equal the velocity of this times 1 second. Because that's how far, when they started moving, that's how far back they would be when they started accelerating. Yes, no. And then you would use, again, you're going to use d equals d naught plus v naught delta t plus 1/2 a delta t squared. And your d is going to be 0 meters. Your d naught is going to be negative v ds times 1 second plus I'm going to run out of room here. Let me move this stuff. Okay. Plus negative v ds delta t plus 1/2 a delta t squared. Yeah, and I think what you're going to end up is you'll find delta t, and then your answer will actually be delta t plus 1 second will equal your answer. Because this will be the time, delta t you find here will be like the time for the speed, time for the police that they're moving. Is that how you, who did it, which way? Or did nobody get it? I kind of like this way with the relative velocities. So I think I'll take a second and make sure mine works this way. All right, so we're going to look at number 12, looking at a seatbelt. Uh, 30 G's, 1 G being that. So, this time why don't I just pop. I'm going to use this friendly little equation because they're talking about the distance that the person can move through. And again, of course, they nicely give it to me in kilometers per hour, right? Seeing if I can convert. But my final is going to be 0 squared equals, and then whatever your initial is, let's see. batteries and then calculate that very slow. So I have 111 kilometers an hour. And so I get 30.8 30.833 meters per second. Plus 2. Now this is, since I took, these are only speeds, but I'm going to use a negative here for the acceleration. So negative 30 Gs, which is 30 times 9.80 meters per second squared. And then I'm going to label that as delta x. And I'm solving for delta x. So let's see. I get 1.62 meters. Which seems reasonable, right? Seems in the realm of realities. Let's see. All right. Falling stone takes this amount of time to travel past the window this tall. From what height above the top of the window did the stone fall? Ah. Good old. I like this problem. I think that's why I always assign it. So you've got your window down here, looking at the rock at 3 locations, and we'll call this H, call this W. We know that its initial velocity was 0. How from our problem do we know that the initial velocity was 0? Yeah, it doesn't actually say that. I wish they had said drop, but we have to assume that. And they told us, what, delta t here? Like 203. And it's 1 point. I don't even need to put W here. 1.30 meters. And we also know that the stone is in free fall, so its acceleration downwards is 9.80 meters per second squared. Right? Hello. Yeah. So, what I would suggest doing is figuring out this velocity at the top of the window, and then working backwards and finding the height that it needed to drop from to reach that velocity when it gets to the top of the window. All right. You could also do it on a sliding graph and say, well, I'm looking for a section where it can go 1.3 meters position-wise in 0.23 seconds, 0.203 seconds, and that will tell you where you have to slide that graph on the axis to get it also at 0. But algebraically, I'm going to use our friend again. D equals D naught plus V naught delta T plus 1/2 A delta T squared. Which direction you guys want to label as positive? Down? Okay. I like that. I'd rather have down positive in this. So, I'm also going to bring these two together so it says that delta D equals, no, I don't want to do that. Never mind. Let's call this height, call this 0. So we end up at plus 1.3 meters, starting at 0 meters, plus VT times 0.203 seconds, plus 1/2 9.80 meters per second squared. Ran out of space, so let's move that over. 0.203 seconds squared. Solve that for the velocity at the top of the window. And then I can say, okay, well, if I know that, I'm actually going to do it with using using V final squared equals V naught squared plus 2A delta D. My V final will be my V top. My V initial will be 0. I've got 9.80 meters per second squared here. And my delta D will be my H. And that'll tell me how high above. Questions, quandaries, wonders why I did it that way. You guys are so quiet. Yep. Yeah, because why not? 0 is arbitrary, right? And that just made it easier to do the blue equation. Or I could have set the top to be -1.3 and the bottom to be 0. Right? Or I could have set the very top to be 0, and then those would just have H and H plus 1.3. Yeah.